Hello and welcome to this webinar. We will be starting now, but could I get confirmation from some of you in the chat room, please? If we can, you can see the slides. Okay, thank you. And I think the sound is working. Any more confirmation if the sound is working and you can hear me clearly? Thank you, thank you. Okay, that's good. Okay, hello and welcome to this webinar. This is one of the webinars that is delivered by ECT Engineering College of Technology, and today's webinar will be talking about the concept of microgrid and energy decentralization, and just want to go through a few of the instructions for all of us in terms of running this webinar. So for the some questions that are coming after each webinar is will you get any copy of the slides or video recording? So the answer will be in front. Everyone registered for this webinar will receive a copy of the PDF slides and also a link for video recording within the next 2 working or business days. And also, if you attended this webinar, you will be able also to get a certificate of attendance, and we are going to provide a link or QR code to a short survey that also will be provided at the end of the session, and once completed you will get the certificate. So just make sure you get that link and also fill the survey, and you will get a certificate for that. So before we talk about the microgrid topic, it's good to introduce you just to the ECT. So we are a dedicated company or an institute ensuring the candidates and the students to receive a world-class education. We are engineering specialists, so we don't deliver other specialists or disciplines. We are just focusing on engineering. That's why our curriculum are industry driven curriculum, where we have some sessions, we have some labs, and also the topics that we choose in are very linked to the industry. So ECT is a branch or affiliated by another established engineering institute, which is called EIT in Australia, and it's an engineering education specialist, and it provides professional certificate, bachelor and master degrees as well. So we are running master of industry and automation, and master of electrical engineering, and also bachelor in power and energy system, and also in industry and automation. So if you want more information about this, you will receive it after also the presentation. So about the accreditation, we are accredited, and the team that delivered this webinar or this programs here, they are one of the best selected lecturers in terms of they hold the teaching awards and teaching qualification, plus the expertise in engineering. And the delivery style, we are online basically, so it suits more of the candidates that they are outside and they want to get this award. Now for ECT, it's running from the United Kingdom, and I am in the United Kingdom now delivering this webinar. So you have a Q&A tab in the room. You can post any questions in that tab, and I will answer them after the webinar. But for now, it will be just a presentation. Okay, now let's get started and start with the webinar. So the webinar today will be about microgrids. We will introduce you to what is microgrids, which is a start of the concept of energy decentralization and what we mean by decentralization and what we call smart grids. Now, the presenter is Walid Issa, which is myself. I am associate professor in power electronics and worked on microgrids for a few years, even during my PhD in the UK, where we developed solutions for power sharing between different energy resources or distributed energy resources. So I'm checking from time to time the tab if there is any issues, or but I will keep the Q&A to the end of the slides. Okay, let's get started. So we'll talk first about the traditional power system and electrical grid, where we have a power station to generate power. That power station traditionally use coal or fossil fuel, petrol, steam turbine. They convert the thermal energy from the basic resources like coal and burning oil, for example, and they generate, for example, steam. That steam goes through steam turbines, maybe 2 or 3 steam turbines, and then they run the generators. These generators will start generating voltage. That voltage might be in the range of a 25, for example, 1000 volt here, and that needs to be stepped up. That's stepping up because they want to reduce the losses by stepping up the voltage, and that will reduce massively the current. That current will go through these transmission lines, but small current, not like the first one that has been generated, and then go through some series of also transformers until we get to the distribution point where we step down the voltage from high voltage to low voltage, and that low voltage is what is delivered to our houses. Some of these voltage might be still high to go, for example, to institutes and business infrastructure like factories and hospitals, universities, and it goes to them as a 3-phase system. But for residential consumers, it might go to them as single phase to 40 volt, for example, in the UK to 40 volt, 50 hertz. So this is the traditional structure, and this is what we call its centralized structure, because we rely on the power station here. That power station may be based in London, and we are going to transfer power few kilometers or thousands of kilometers to the north and south. So we rely on a lot of transmission lines to deliver that power from that power station to the consumers, maybe in the country. So that is called centralized structure, where we rely on one entity to support or supply that power. If there is any storm, any accident, any problem happen to this transmission line, a lot of people were gonna suffer and gonna lose the supply of power because of this kind of system. I know, and maybe some of the attendees know, that we have different network structures, maybe ring and radial. Maybe the ring might reduce and mitigate the risk of losing one of the power supplies feed and might compensate from others, but we still at the last point when we deliver to the residential consumers, we still have one feed here, and especially that feed, if there is a problem here, for example, that also will cut the power to the consumer. So these are the kind of problems and limitation in the previous system, which is called the centralized energy source. So And the points that we are going to highlight here are the dependency on a high capacity fossil fuel. That's one of the problem. And we know nowadays the carbon emission and the impact of this carbon emission on the atmosphere and also on the climate change and the increase of the temperature of the earth, that will increase also the sea level and makes a lot of change in the climate, and this has been observed. Increasing also the carbon emission, which has been also mentioned here. Getting a large amount of power in one place, so we have thousands of mega or hundreds of gigawatt in one place, and we rely on the transmission line to take off that job to transfer it to the consumer. So if something happened to that place, okay, we are under the mercy of the other, for example, feeders and other power stations. Using a long transmission lines as well, that means losses, and it's not economic at some occasions and some cases, and has low reliability against sudden faults. If a storm happened, if there is, for example, any political or maybe a war happening, that will also make the transmission line under the risk. So what is the solution that has been for about a decade now? Is called the microgrid, where we don't have just centralized power plant, but also we have different power stations or power plants. We can call them small distributed power plants. For example, they can rely on wind on the right hand side corner here, and maybe they can rely on virtual power plants, like for example solar panels here, or fuel cell, or any other, for example, generators that called, for example, renewable energy resources. So what we have here in the middle fuel cell, we have CHPs, we have solar, we have houses that can generate solar system or solar power, and also other resources. So what we're doing here, we are reducing the dependency on the central power plant, and even if there is happening any problem, we are generating locally some power that can make the consumer survive. Okay, that's one. Second, the transmission line will not be stressed like before. So the transmission line from the central power plant, they don't need to deliver that amount of power, that amount of current to the consumers. Okay, so the microgrid here is a group of consumers plus their generator. Okay, and maybe nowadays the solar system is very popular in the UK, and every, for example, a few houses, you have one house that has solar power with the storage as well, the battery system. That means they don't rely on the centralized power plant anymore, or they relied on some time, and even if there is any cut in that power, we still have that amount of power locally generated every day. So what is the benefits of microgrid in this case? Yeah, it gives us the ability to integrate renewable energy resources. It gives us control of the flow of power. So I can, for example, as a customer, I can have my solar to, for example, sell it to the grid. We have the ability in the UK to sell power, excess power, into the grid again. So we can sell it, or we can store it, or use it locally. Reduce the carbon emission because we don't use the centralized power, that amount of power supply anymore. So they can, for example, at some time of the day, they can switch off one of their synchronous generators, for example. And that will reduce the losses because we don't consume that much of power like before, that goes through a transmission line. Reliable against sudden faults. So if a fault happen, we still have locally some generated power. And the most important part is the customer. Customer is not just a receiver now. No, it is part of the game, part of the grid, part of the flow of power between the grid and the customers. So the customer might, for example, and maybe in the future, might help, for example, neighbors to sell his excess power or their excess power to the adjacent regions, for example, by different prices. And this is what we call peer-to-peer energy market. So that is the what we call the transition between the centralized grid, where we have centralized power station that goes through a transmission line to the customers and business entities, to microgrids, where we have part of the customers, they have their own energy, they can supply each other, they can supply themselves as well, and also the excess power can be pushed to the grid or can be sold, for example, to other region. So this is what we call microgrid. And as we see here, we have also the integration of renewable energy. So how the microgrid works? The microgrid diagram, the simple single phase diagram, is look like this, where we have, that is the switch. This is the switch where we connect the grid to the body of the microgrid or no. Okay, what we have here, we have some small DC generators, for example, to that microgrid. For example, part of your city, or maybe some parts of the streets. Okay, they have one DC generator to supply them. They have loads, okay, and they have some other people. They have wind and energy and solar systems on top of the roof. These transformers might be there. It depends on the voltage and level of voltage they have in the bus here. So this one here is called the microgrid. Okay, there's a choice to connect that microgrid to the grid, and or maybe disconnect themselves from the grid. So this is the microgrid here, and that is the source, which is the grid, and this is called the switch that connects the grid to the microgrid or isolated. So in this case, we have two modes. Okay, we call when we connect the grid to the microgrid, we call that mode the grid connected mode. And if we just open that switch, we are isolated, we call it island mode. Okay, so we have a grid connected mode and we have island mode. Okay, the island mode have different names, like for example standalone mode or off-grid system. Okay, you are running without the grid, so we call it off-grid, but the popular name is island mode. Okay, so when you, for example, have a book about microgrids, you will hear a lot about a grid connected mode and island mode. Now in a grid connected mode, if you switch on this one, you close it here, your bus now is dictated and dominated by the grid. So the voltage, the frequency here will be fixed by the grid, and all the resources will be interfering or interacting with that grid by supplying more power or less power, by watching what is the frequency and voltage here. Okay, but in island mode, that will be controlled by, for example, diesel generator or one of the battery storage system. Okay, for the interface, for each battery, for each energy source, for example, if it's wind, if it's tidal, if it's solar, all of these are can be classified as DC, and some of them are AC, but also they can transfer to DC. Okay, we store that power in battery, and then we use something called inverter. That inverter will convert the DC to AC, and that AC now will be connected to where? To the bus. Okay, that bus of the microgrid that can be connected to the grid or can be isolated from the grid. So that can supply our home, or we can connect it to the grid and sell power. So this is one of the examples of how we integrate solar panel into the system. So we have solar panels here, and solar panel, they have something called operating point, maximum operating point. That operating point need to be found by charger, and that charger charge battery, and then that can supply some DC load or can be converted from DC to AC load. So this kind of structure is the traditional structure for PV in the UK. Okay, so they have this kind of structure to convert, and that power to the AC load here, that can be sold also to the grid. The inverter, when you look at the inverter, it's a group of power switches, and what we have here, we call it IGBTs. That IGBT here is they are receiving something called PWM. That PWM switching on and off very fastly. That power that comes from a DC source, for example, a battery or wind or PV, and they convert to AC. But because we are switching here very fast and the waveform will be square, we filter it by something called LCL filter, which is inductor, capacitor, inductor filter, that will rid of all the harmonics. And then here at the right hand side, we will get a pure sine wave, exactly like the grid. And that will supply to the grid or will be provided to the local load. We have also few controllers here just to stabilize the voltage to be at the proper RMS and frequency. We have different topologies for that inverter. For example, if we have PV and PV has low voltage, we can use DC to DC converter to boost up that voltage to a higher value, for example, from 100 to 400 volt. And then the DC to AC voltage that takes 400 volt DC and convert it to the voltage that suits the grid, maybe 230 volt RMS. Or we can convert the PV from DC to AC, okay, using an inverter straight away, but low voltage, and then we step up the voltage using a power transformer. Or we can use isolated DC to DC converter, so still DC-DC, but it's isolated, okay, that will reduce the amount of losses, okay, and then that DC will be also transferred to AC. Or we use just one stage here, okay, that stage convert DC to AC, and that will happen if you have enough voltage from PV. So you have very big PV voltage that's enough to convert it to AC. But at the same time, we have to seek for maximum power point tracking as well. So these are different topologies for the inverter, and the literature can use any of them, depends on how much voltage they can get from the solar panel, for example. So that structure uses DC post to step up the voltage, and that structure uses transformer to step up the voltage, and this structure here uses transformer to step up the DC voltage. And maybe the transformer, how it steps up the DC voltage, they convert it to a pulsating voltage, okay? So they don't step up the DC as DC, but they convert it to a pulsating voltage at high frequency. The transformer here will be smaller size than this one here, okay? And this one is kind of one is used normally in the inverters. And if you have many PV to step up the voltage, that will be using this one. So these are the nodes to be included. Again, as I mentioned, the inverter is a group of IGBTs that will take some power from DC source, for example, battery, and they filter out using filter out the harmonics using LCL filter, and then they transfer that power to the grid. And what we have here, we have to provide control. Why I'm mentioning this? Because, for example, some people in master level or PhD level, they focus on this only, the controller. They have to measure the current and voltage, they have to provide synchronization with the grid, and they have to calculate the power. What kind of power we need to calculate to manage the PWM generation, the active and reactive power. So, for example, we designed before one inverter, and we stick with these, for example, these values, 1 millihenry and 50 micro farad, for example. And for sensing, we might use LEM sensors, for example, to measure the voltage and current. For the controller, there are a lot of controllers available. So one of the most popular is the TI Texas Instrument DSP microcontrollers, this is one of them. So this is just for knowledge about, okay, if somebody wants to develop their own inverter that is able to integrate in renewable energy, you might prototype one, very robust one, using these kind of components. So the same structure that we feel using it for integrating, for example, PV and renewable, you will find exactly the same structure in the electric vehicle. If you look at the electric vehicle here, and when we mention now inverters, boost converter, all of that is power electronics. And we have maybe in January, we have another webinar about basics of power electronics. So what we have here, we have battery, okay? That battery here, high voltage battery, it might be 400 volt in the electric vehicle. For example, in Toyota and Mercedes, they have 400 volt battery, and in Tesla as well. They need to charge it, so that's why they have onboard the charger, and they take power from outside, they charge it. They take that 400 volt, for example, and they supply some auxiliary units. For example, the microcontrollers, the horn, the lamps, all of these need less voltage, so they step down the voltage. Or they can leave that voltage here, okay, and they boost that voltage. If it's low, for example, if it's 200, they boost it to 400 and supply to the inverter, and that inverter will run what? The motor. So the DC supply here has been boosted, stepped up to suit the inverter, and the inverter might need 700 volt, for example. So if you have 400 volt and that inverter needs 700 volts, so that we need a boost. And then they run the machine, okay, that might be induction machine or BMS machine. So they use inverter to generate that power. So we convert it to AC, and that runs the vehicle. What we see here, exactly the same structure. We have battery, we might have here solar panel, okay, that convert the power to battery, and then we need boost and inverter. And also, instead of electric vehicle here or electric motor, we might have house. How to calculate the active and reactive power? This is one of the examples that we used before. We have the voltage, we measure the voltage, okay, we measure the current. And to get the power, we just multiply the power, the voltage with the current. So that voltage with that current, multiplication, and we run it through a low pass filter to minimize the fluctuation, and that will generate power. But to generate reactive power, and I think our maybe reactive power is known for all of you. Reactive power is the imaginary power, or that consumed by the machines and any inductive or capacitive load. So that can be calculated by shifting the voltage signal by 90 degrees and then multiplying it by current, and through low pass filter we can get the reactive power. So every inverter has to calculate active and reactive power and try to make the active and reactive power based on the presets that they have. So about the PWM generation, for the IGBTs, we use this block where we have triangular wave here, and that triangular wave is compared with the sinusoidal wave, and that will generate here pulses that goes to the IGBTs. These pulses, if you filter them, you will get sine wave. So if you want, for example, square wave or triangle wave, you just supply square wave, triangle wave here. That will be compared with this triangle wave, and that will generate pulses. After filtration, you will get exactly the signal you want. But because we want sinusoidal, because we want sine to integrate with the grid, they have to have same shape, same frequency, same amplitude. So that's why we have to get sinusoidal wave PWM. And this is one of the waveform here we got for example. So in these coming slides, I'm going to shed some light on the microgrid literature and some of the aspects that maybe you will work on, for example, in your study, or if you are interested for more degrees, you can, in master or PhD, for example, you can focus on one of these points. So the voltage and current generation from the inverter, they have to be sine wave and low distortion. No resonance, regulated voltage, smooth step response. And how to do that? We can use some controls like PI, PID, or resonant controllers, adaptive or repetitive controllers. They are established now in the literature, so you can use one of them, for example, to stabilize the voltage and make it without distortion. So about power sharing, as I mentioned, we measure the power, active power and reactive power. So for example, if you have solar here, if you have a neighbor house with the wind, another neighbor house with solar, how you make sure that they are not overloaded and one is sharing power more than the other. So we provide something called power sharing. That power sharing is, the goal is to provide adequate power sharing, so everyone share power to the grid or to the load based on the capacity of that inverter. Okay, accurate power sharing, so if I want to push 1 kilowatt, for example, I push 1 kilowatt exactly, not more, not less. And we want to try to do that without communication. So for example, we don't need communication between different inverters and each other, and we wanted very smooth step response. So we don't want oscillation and resonance. How to do that? We have, for example, master-slave controller where we communicate between each other. But because we don't want communication, we use something called a droop control. Droop control is a control that drops the frequency based on the power we want to inject. Because the frequency of this bus is 50 Hertz. But if I make that inverter, for example, to reduce that frequency a little bit, they will push more power to the grid. And by controlling the frequency reduction or droop, okay, you control how much power you are injecting to the grid. And this will give us accurate and adequate power sharing. So the droop control is like we have one generator and another generator. How I make my inverter at my house and maybe other inverters at different houses, for example, if we want to share and supply power to a load, how we make a control of each one power, that is described by droop control. The goal is also not just to provide active power sharing, we want also reactive power sharing and reactive power control, and that is one of the disadvantage of the droop control. They can't really guarantee accurate reactive power sharing, okay? And they want to have low harmonics, so that's why we have here inductors and a smooth step response. How we can use that? There are other proposed solutions where they use extra loops or sometimes communication to provide accurate reactive power. So there are something called islanding detection. From the name, islanding means we don't want to connect to the grid, okay? But if we are connected to the grid, but the grid has a problem now, the switch opened, the fuses or breakers already now opened. So how we detect that we are shifting to island mode? First question, is it important? Yes, it's important. Why? Because if all inverters thinking that they are pushing power to the grid and the grid is not anymore there, the microgrid will destabilize and trip all the units. We don't want the units to be tripped. So we have to detect there is islanding happening, there is a grid absence or grid failure, to isolate ourselves from the grid and work locally as island mode. So we want to detect the islanding to work in island mode, not a grid connected mode, to change the mood. So the goal is to detect the grid absence within 2 seconds. Why 2 seconds? Because this is the IEEE standard. They have to detect the islanding or island or a grid absence or failure within 2 seconds only, and the switch to island mode. And there are proposed solutions like, for example, passive methods, voltage frequency deviation. And how they do that? We know that if the grid is there, if the grid controlling the bus, the frequency will not shift at all. It will be 50 Hertz exactly. But if each inverter tried to shift that frequency, okay, the frequency will not shift because they are dictated, they are controlled by or dominated by the grid. But if the grid is not there, the frequency will shift. And if the frequency shifts, that means there is a sign of grid absence. So this is one of the methods. They call it passive. Or active, they provide, for example, or they inject some harmonics to test if the grid is there or no. But the most maybe passive ones is the frequency deviation. Frequency deviation, you push the frequency a little bit outside the limit. If it comes back, that means the grid is there. If it doesn't come back, that means the grid is absent and we switch off. The management for microgrid is not really one layer of management, but we have 3 layers. The primary control, where each customer has the control on the active and reactive power. But we have also secondary control, where we restore the voltage to help the grid to restore the voltage and the frequency. And we have the third controller management, supervisor control, where we establish, for example, a management system for the energy during the night, during the day, which one should provide more power or less power, and that dictates the prediction as well, and load shedding. Okay, so if we don't have any more power and we have to shed some loads, turn off some load, that's the responsibility of this control. So we have 3 levels of controllers. One level can be controlled by the customers, and others should be controlled by the grid operator. So one of the points that I personally worked on is called the paralleling inverters operating in island mode. I want to reduce the circulating current between inverters. We don't want, for example, my power that I'm generating to go for my neighbor by error, okay, by mistake, by mismanagement. We call it circulating, okay. That might happen if we have a very tiny deviation and you are losing that power without paying, or you are destabilizing the system. Okay, so we want to reduce the circulating power. We want to have a good power sharing in island mode. Island mode, again, we have a few inverters together. We want to make them all share the power without problem. Smooth transition between grid connected mode and island mode, and to manage the stability. So this is one of the things that I personally worked on. We have 2 generators, okay. These 2 generators, they generate DC regardless of what they are, okay, and we convert that DC to AC, to DC, another step up voltage here, and then we convert it from DC to AC. So what we have one unit here and we have another unit here, okay. That unit is called unidirectional because it can push power to the right to the bus, but it can't consume. The same thing here, but this one is bidirectional. Bidirectional, it means it can absorb power to charge the battery, or it can push power out, okay. And we have this switch that can control if we are on grid or off grid system. So what we have here, we have the unit controller that manages the primary control level to generate PWM and calculate the power and manage the drop control. And they decide here how much power we need to give to the grid, okay? And the other unit here as well, how much power I need to give to the grid, or how much power I need to get out from that grid to charge my battery, okay? And we have central control with a slow communication. Slow communication means I don't need to use that for managing the power between them. No, I just use that for monitoring, okay? So what we have here, we have that switch. If it's on, that means I can sell power to the grid, okay, or I can consume power to manage my power here, to charge my battery. If the grid is not there, that unit and that unit should be aware. That's why we need islanding detection. And also they have to manage the power between themselves to supply a load if we have a load here, or to, for example, this one to charge this battery. If that battery is fully charged now and we don't want any more power, they need to manage themselves to switch off or reduce that power, okay? Without doing this, this bus will go unstable. The hertz and the voltage, and both of them will be tripping, okay? So that's why some management between them is very needed. So in my study, for example, I assume this is stable and fixed, and the methodology for running this kind of research, you need to model the microgrid mathematically, you need to propose a controller, you might use software like MATLAB and Simulink, which is very essential, and then you go for practical implementation. I did all of that and even build a microgrid like this. These are 2 inverters with some LCL filtration. That is the inverter from Semicron, that's another inverter from Semicron, and we have a LIM voltage and current sensors, and finally the switching, the PWM switching. And these are kind of other interface just to and load as well to control the power. This is also the GUI. You see the voltages, and you can see the active and reactive power from this as well. So this is just an awareness about, okay, how we run this kind of experiments. So that is some results. So we are able to generate, for example, an AC. We run it at low voltage because we don't want to exceed, we don't want to go for high voltages. We just have some test on 30 volt only on lab. The total harmonic distortion was 1.8. If you don't know what total harmonic distortion is, the amount of distortion in the AC, how close we are to the pure AC. Okay, now that is the AC that has been generated from an inverter. But when we look at the reactive power for the two inverters, one is giving about 35 var and the other one is absorbing about 15 var. That's not good, because they are, one is consuming and one is giving. We want them to be the same, and that's why controllers that we need to manage, we have given here, we propose some controllers that will reduce the difference between them and make them equal as well. So this kind of research that can be done by master student and maybe a PhD student, for example, to manage microgrid controllers and power sharing between themselves. So the keywords, if you are interested, you can look at in Google, research in group control, voltage and current, reactive power sharing, island detection, supervisor control, MPPT for solar inverters. Look at these keywords and see if they are really one of the interest. At the end, we want the customer and their buildings to be part of the game, part of the power flow, part of the story of the grid, okay? Using the renewable energy resources to manage the power locally and to charge their electric vehicles, and if there is excess power they can sell it to the grid and they can consume power. For example, in the UK here, we have during the daytime we have a high tariff. High tariff means high price of electricity. In the night time, after 12 o'clock in the night, we have very low, cheap prices for the electricity. That means we can manage our loads to run in the night. I can charge my electric vehicle in the night, but I can sell my renewable energy source in the daytime, okay? Or I can store it as well. So that will bring some benefits to the customer. They can reduce or the bill, or even they can generate income as well based on the tariff that exists in the country, okay? That's, I think, everything about what is microgrid and why microgrid and what kind of research sometimes happening. It's maybe higher level knowledge, but that is the webinar about microgrid so far. I hope it's clear, and if you have any question, please post your questions to the chat or Q&A, and I will try to answer them based on my knowledge. Thank you very much. So please, if you have any question, please share them on the Q&A tab. Avoid the chat room. Q&A is better. Yeah, I will give a minute just to check. Okay, so one of the questions, what is CHP? CHP is combined heat and power plant. Combined heat and power. Does it mean the coupling all will be in one bus bar? Yes, all of the inverters will be on one bus bar, okay? But the ATS will be at the switch. Okay, the ATS will be at the switch, but I have to clarify something. There is nothing called ATS in microgrid. Why? The ATS is just for auxiliary diesel generators that are not running, and they will run if the grid is absent. But in microgrid, we have these switches. We have the inverters always running in microgrid mode, or or a grid connected mode. So if I go back to the first graph, yeah. So here, for example, you have all these units here are already running. They don't need to run just because there is no grid. Okay, so that's why if you have, for example, a diesel generator that's not running at all, and they will run just in case the grid is absent, you need ATS here. Okay, but you don't need ATS in normal microgrid running on inverter only. The slides will be shared. Yes, will be shared. Does the inverter replace the need for transformers? No, the inverter, the transformers are still needed. Okay, it depends on the level of the bus, the common of point coupling here. Okay, so if that common of point coupling is 230 volt, you don't need these transformers. But if you have, for example, a few kilovolt, you need the transformers. Okay, so it depends on that bus. Is it distribution bus or is it a transmission bus? Meaning of DIP. Not sure where we see DIP. Seems I can't escape power electronics. Yes, power is essential. However, some of the researchers and the study and maybe students, they just focus on the higher level. They don't need to work on power electronics or switching at all. But if you want to know everything, you have to study everything. But some people, they just focus on the layer of energy management only. So don't worry about this. You choose where you want to focus on. If you put, that's a question, if you put solar panels in series or in parallel, which one gives higher power? The power doesn't depend on if you connect them series or parallel. The power depends on how many panels you have, how many modules you have. If I have 10 panels that again can give me 1000 watt, these 10 panels, if you series them, parallel them, or mix them, they keep that 1000 watt. So regardless of the connection, you will get that power. DC to DC converter can be done with or without transformer. With a transformer, they call it isolated DC to DC converter. Without transformer, they call it a non-isolated DC to DC converter. So both are topologies are already existent in the literature. Difference between transformer based and transformerless, it depends on the voltage generated by the inverter and also the voltage of the bus. If you are going to generate 230 volt, for example, and the bus 230 volt, you don't need transformer. Okay, but you need high DC value. But if you need to step up the voltage because of the bus is 1000 volts, so you have to have transformer. The need of stepping up DC voltage because the inverter has a minimum voltage to accept it. For example, they need 200 volt or 400 volt. For example, the electric vehicle, the inverter in electric vehicle needs 700 volt. In this case, I need to provide 700 volt DC. Okay, I have to boost the voltage from 400 to 700. It's good to use, guys, the Q&A tab, not the chat room, to boost the questions. Yes, we will share the slides. Okay, let's go to the Q&A. Does the inverter replace the need for transformer? No. The transformer sometimes is needed if the amount of voltage, the level of voltage from the inverter doesn't suit the load or doesn't suit the bus. So we have to step it up. So it depends on the inverter rating. AI and machine learning can be incorporated in the energy management layer. We have few management layers, as I described: primary, secondary, and territory. So in the third part here, the AI can be used for prediction of the load, prediction of also generation, and based on that they can schedule the load shedding, for example, or maintenance, or maybe they can even provide different prices for the electricity for customers. Yeah, we need more power here because a lot of consumers turn on their air conditioning or heating system. We need more power, for example, at that point, at that hour. So they make it high price, more incentive to the customers, or make the opposite. So it depends on the tariff and the behavior of people in the country when they turn on the devices and turn off, and based on that they decide the prices. So AI can help in this. In place, two hydro generators. You find one generator is unable to share the load and they are connected in parallel. What could be the problem? Might be the regulator unit. If it depends on what are they identical? Are they designed, the hydro generators, are they designed to work in parallel and share power or no? Sometimes you have to play with the settings to make sure that they have exactly the same droop controller gains. So we have something called gains, which is parameters that they tune and manipulate to make the power sharing between two identical plants the same. If they are not the same, the power sharing will be different. Principle of CHP, it's not the proper time to work on principle of CHP, but it's combined heat and power. So they rely on some heat resource, for example, a fuel, cool, to generate power through steam turbine, and maybe also they have another power generator as well to make them combined, and then they send it. So for example, in one of the master program modules, we have that concept done in or explained in details. STC is the state switching. So that switch is connecting the grid to the microgrid body, or isolate that grid from microgrid. That's the STS. So it's a switch, but sometimes they call it STS, maybe state switch. Okay, but regardless of the name, because we have different names in the literature, regardless of the name, its operation is to connect the grid to the microgrid, or to isolate it, to work on a grid connected mode or island mode. Yes, we are accepting PhD candidates based on if they are sponsored or if they are self-funded. But we don't have currently scholarships, so you can contact me later to check. If you have any question, please post it in the Q&A, because I can't unmute any of you. So it's better to post the questions. Okay, I think I answered all the questions now. Is there any others? Okay, if you want, I can share my email in the and you can also ask the organizer to share the email of me. I will share it now in the chat room to just post any important emails, please, about, for example, the program, about the PhD, and about other things related to the program or the topic of microgrid, I'm very happy to answer. So my email is in the chat room for all of you to have it. Yeah, there is a question about if this technology has been deployed somewhere. Yes, there are some countries, they have deployed this technology. In Denmark, I think North Europe, Germany, I think they have already successfully demonstrated, and in Spain as well, demonstrated a very working principle of microgrid. Maybe that was happening maybe 7 years ago. So and in China as well. So I think yes, the concept has been working for a few years with no problem. About the security, this is another side of the story, to be honest, and maybe it depends on what kind of security you mean. Is it energy, or is it technical, or, for example, from hacking, from it depends. From hacking, from, for example, cyber attacks, I have no knowledge about these because my expertise in power more. But I think yes, it's another important aspect. Why? Because, for example, in conflicts, political conflicts and these things, so they attack now by cyber, and they might switch off all the microgrid by just a bug, okay, or virus. So yes, that's another aspect. But if you mean by security, the energy security, this is our part. We have to have controllers that manage the power, that prevents the grid to go to unstable, okay, and that is the rule of us. The disadvantage of a microgrid, we can't call them disadvantage. We can call them challenges so far. The challenges are the accurate power flow between the inverters to the grid and the smoother transition. These are the goals. We can't call these are challenging goals because in the centralized traditional method of power, we don't have these problems because we have one power plant that is managing everything, okay? The bus regulation and voltage frequency, we don't have an interaction with other resources. But because we have an interaction with other resources now, and we have to build a small entity for energy, that will provide also some challenges in power. And that's why we shed some light on what are these challenges. Yeah, I mentioned this. The power electronics part, is it costly or complex? Yes, it's complex, but nowadays the industry have already now established a good mature systems. They have good inverters, and that runs for years and years. The prices of semiconductors maybe spiked during the COVID, but nowadays they are going down. Maybe from now to 10 years later, the prices of power electronics and the complexity will be acceptable. So we are talking about the next coming 10 years. We are not talking about now. Now this is a development on the microgrid system and how they can integrate renewable energy source, not just to the customer, to make it interacted with the grid. Okay, guys, I thank you very much for all of you. I enjoyed talking to you and listening to your questions. I think the last question is the microgrid compatible with biomass energy source? Biomass, I don't know if it generates DC or AC. Okay, biomass is finally, I think they might generate gases and these things, and you might use that kind of burning material, okay, to burn and boil water and the steam turbine, and you can run generators, so it's AC. Yes, you can integrate it, but not through, I think, inverters. Okay, if they go through steam turbine, so I think the integration will be different. Okay, but if they are rectified and then we have to use inverters, so that's the case. It depends on what technology of biomass and how they generate power. Okay guys, thank you very much. We will share, just give me a second if I have that, the link for the, yes, for the, if you want to get certificate, please go through this link, okay, fill the form and you will get the certificate, okay. So I will leave it everywhere, post it here as well. And happy to see your feedback on the webinar. So I just post the link again. I will stop sharing now. Okay, thank you very much all, and please take the link before we close. We have about 40 attendees today, so we hope that all of you get the chance to know what is microgrid. Okay, I will close in a minute just to give you a chance to click on the link and save it somewhere. Okay, thank you very much and see you in the next webinar. Thank you.